Hello, Life. Hey, welcome to the next talk at Meeting C++ 2025. Now it's going to be about lock-free keys and designing them, and that's a very interesting topic. Very much looking forward to your talk, Quasar. Please take it away.
Hi everyone. Welcome to my talk on designing lock-free queues. Uh, we are going to have a bit of a rundown on what concurrency and threading primitives are offered by C++, and then we'll dive straight into how to write a lock-free queue. So let me start by talking a bit about processes versus threads. As you probably know, a process is just a running instance of a program or code. It'll have its own set of resources, memory, file descriptors, and the execution context. A thread is a construct which runs within a process. Uh, Threads share the same address space as the parent process, including file descriptors, heap memory, and any global data structures. Sharing memory space between threads is a challenge, right? Because when you want to share some data between threads, you need to ensure that data is modified in a consistent way, and the integrity of the data is not lost. In order to prevent data corruption, threads employ certain synchronization mechanisms. The ones offered by the C++ standard are locks and mutexes, condition variables, semaphores, latches, barriers. And we'll have a brief walk through these. Um, Multitasking, you would have heard the word multitasking. So multitasking comes in two flavors. One is called as preemptive multitasking. Preemptive multitasking, as you know, traditionally involves some hardware timer interrupt mechanism, which is going to interrupt the current process and brings in the OS scheduler to determine what process should go next. The other form of multitasking is cooperative multitasking. And C++ now supports cooperative multitasking using coroutines, which means simply that a function can be paused and resumed at any specific point, and a thread or a function can voluntarily relinquish control to some other thread. Uh, I'd like to just talk a little bit about how do you create threads in C++. So here are a few ways to do it. Um, you could directly pass the function name to the thread constructor, as on line 6. You could have a lambda function, and you could pass the name of the lambda function to the thread constructor. So it accepts lambdas. It also accepts anonymous lambdas, as shown on line 15 to 17. You can also have function objects, which are basically like classes with a function call operator. So you can pass an instance of a function object to the thread constructor. And finally, you can invoke. You could have a member function of a class, and you can pass this as the work package to the thread. And to do so, you use this syntax. So you would say class name, scope operator, func, and you would actually also pass an instance of the class. Moving on, whenever you create a thread, C++ expects that either the thread is joined or detached. The join function essentially says that the parent thread will block on the current thread and will wait for it to complete. Only when the child thread completes, the parent can go ahead. So it's a blocking call. Um, uh, there is also something called as detach. So detach is used whenever you want to run background threads. Now let me just focus in on this example. So um, you can query a thread to see whether it's joinable. Um, and to do so, you would invoke the joinable function. So on line 11, I've created a thread T1 using a default constructor. Um, a thread created using the default constructor is never joinable. So this is T1.joinable is going to return false. And then I create another thread T2. I pass the function func as a work package to T2. It's going to, and what I do is then I swap the work packages of T1 and T2, right? So T1 now points to the work package func, and T2 doesn't have any work package at all. So a thread with a work package is obviously joinable, and that's why T1.joinable this time is going to return true, whereas T2.joinable is going to return false. When the main thread invokes T1.join, it is now going to block on this line. So line 7. So on line 17, the main thread will be blocked until the join function returns, and it will wait for T1 to complete its task. Obviously, once a thread has been joined, it is no longer joinable. So if I query it again and ask if T1 is joinable, it's going to return false. Moving on, I was speaking a while back about detach. So if you would like to run threads in background, like daemon threads, right? You would use the detach function of the thread API. Daemon threads are often used to run low priority tasks, for example, garbage collection. So out here in the example on the right, I have a daemon thread which keeps checking if the so it's essentially going to run for a few seconds. I initialize the timeout variable to 3, so it's probably like going to run for 3 seconds and then just finish. And in the main thread, I start a thread. I create an instance of a stud thread object with daemon thread as the work package, and I call detach. Now, what will happen is that the main thread will run independently, and it's not going to wait for the daemon thread to complete. There's a nice facility in C++20, which is called the std thread. This is just an RAII wrapper over stud thread. It's as we've just seen, right? When you create threads, it's important for the parent thread or the main thread to call join or detach on the thread. Forgetting to do so could be catastrophic because it would result in the stud terminate function being called and the program gets aborted. So it's important to remember to call either join or detach. Now there could also be code paths. For instance, your thread could throw an exception. So there may be a code path where you've forgotten to call join or detach. So to avoid such cases, you could write a wrapper class over stud thread, which will automatically invoke join on the thread in its destructor. And this is precisely what std thread does. So std thread destructor, calls join on the underlying thread and blocks until the own thread completes. It essentially implements the RAI idiom, and it avoids pitfalls when we forget to use join on a thread. Let me also speak briefly about yield. Yield is a function which will momentarily suspend the current thread and hint the OS, indicate to the OS to reschedule some other thread. So in the example on the right, there is a worker, or there is a work package, there's a work lambda function, which is going to run a infinite loop. It essentially at every iteration of this loop, it generates this variable called as work to do. So you could either have some work to be done or not. And if there is work to be done, then you start doing the work. That is, you complete some portion of the work. And if there is no work to be done, the thread just yields by calling yield method on this thread. This is very commonly used when you want to write coroutines to do asynchronous programming. Now, I'm going to speak a little bit about what is mutual exclusion. Most of the multi-threaded programs, as we know, are going to share some sort of state between the threads. Now, in this example that I have on my screen, there's two threads, T1 and T2. Both T1 and T2 have the same work package. They are going to run the function func. The function func, all it does is it runs a loop which will iterate 1,000,000 times, and it will increment a global variable called as counter. What is going to happen is the counter variable, if there was if there is if these two threads have no synchronization between them, the counter variable will not be equal to 2,000,000 at the end of this program. Now let me explain that a little bit. So the thread T1 runs off, it starts incrementing the counter. The thread T2 runs off, it starts incrementing the counter. If these threads were to run sequentially, we would expect the result to be 2,000,000. However, they are running concurrently, and one of the scenarios that possibly happens when we are incrementing the counter is shown in this table. So the thread is incrementing the counter in roughly like 3 steps. First, the counter variable is loaded into a CPU register. The value in the register is then incremented by 1, and then the value in the register, the updated value in the register, is stored back into the counter variable memory address. Now, if you think of incrementation of the counter as these 3 small substeps, what will happen is these substeps can be interleaved between each other. So take a look at this timeline here. Thread 1 first loads counter value into CPU register. It then increments the register value. So as an example, let's say that the counter value was 10. 10 would be loaded by thread 1 into a CPU register. It would increment the register value, so the new register value becomes 11. Now thread 2 comes in, and thread 2 loads the counter value again into the CPU register, so the counter is still 10. It will load it back into a CPU register. It will also so thread 1 then does the store of register into the counter. So it's going to store 11 in the counter. Then thread 2 proceeds with the rest of the work. So it increments the register values. So it's going to be 11 again. And finally, it will also store the register value in the counter. So it's going to overwrite whatever was previously there in the counter. And the result of this sort of sequencing is that the counter still contains 11, whereas it should have contained 12. So this is what is typically called as a race condition, and we would like to avoid these data race conditions by using certain primitives offered by C++. So one of the primitives is a pseudo mutex or mutual exclusion. A mutex can be thought of as just a variable on which is like a flag so it's just like a flag which you can flip 0 and 1, and a thread must acquire a lock on a mutex. So there's two ways that you can acquire a lock on a mutex. The calling thread can invoke lock, or it can also try on a best effort basis and invoke a try lock. Lock is a blocking call, and try lock is not a blocking call. If whenever a thread owns a mutex, all other threads will block when calling lock. Yeah. So this is the exclusive ownership semantics property of a stud mutex. So this is fairly simple. So on the right-hand side, as a complement to the previous code snip, I have two functions now. One func without locks, and one is func with locks. The func without locks runs a loop 1,000,000 times and increments the counter 1,000,000 times. The func with locks does the same thing, but it acquires a lock on the mutex before doing so, and it then increments the counter and then releases the lock on the mutex. You would typically find that the first scope here between lines 24 to 32, if you were to run this, you would find that the counter would not be equal to 2,000,000. It's going to be a random, it's going to be a number which is non-deterministic. So each time you run this logic, it's going to be some other number, and it's not going to be equal to 2,000,000. The second scope is spawning of two threads with the work package func with locks. So here there is the mutex is being used to synchronize access to counter between the two threads T1 and T2, and therefore it will print a value of 2,000,000 on line 48. There are also cases when we need to let several threads simultaneously read protected data, but just give one thread the exclusive access. And for these purposes, the C++ standard provides a stud shared mutex primitive. Stud shared mutex is designed such that several threads can share the ownership of the same mutex, and they can acquire a shared lock on the mutex using lock shared or try lock shared. To release the lock on the mutex, they would have to call unlock shared. So on the example in the right, I have a reader thread. I have a reader lambda function and a writer lambda function. The reader lambda function is reading the counter value, and it's just not. It's just going to do anything with it, but it's not going to modify the counter. And the writer lambda function first acquires a lock on the mutex and then updates the counter each time it runs. Now, I create a few reader and writer threads. So I've created 4 reader threads, 2 writer threads, and you would find that uh, this this piece of logic is going to work out fine because um, the reader lambda function or the reader thread always acquires a lock using lock shared, and therefore multiple readers can read from the counter variable. With the writers, we are acquiring an exclusive lock using mutex.lock so that only one writer can increment the value of the counter at a given point of time. So I'm going to talk a little bit about some of the problems in locking. One of the problems that often happens is called as deadlock. This is a situation where if you imagine there are 2 resources. Each resource is synchronized with a different to the mutex. And imagine that there are 2 threads. And let's say that for each of the threads, in order to complete the task that they are assigned, they need to acquire or they need to work with both the resources. So if thread 1 wants to finish its task, it should acquire, it should be able to work with both resources, and likewise for thread 2. One possible scenario that could happen here is that thread 1 first acquires a lock on the first mutex, and thread 2 first acquires a lock on the second mutex. So thread 1 now holds the first mutex and can use the first resource. Thread 2 now holds the second mutex and can use the second resource. Thread 1 now proceeds to acquire resource 2, and it tries to acquire a lock on mutex 2, but it is going to be blocked forever waiting for the second mutex to be available. And the flip situation occurs with thread 2 because it will be blocked forever waiting for the first mutex to be available. So this is like a deadlock situation, and both threads will be blocked forever waiting for each other to release the required mutex. One possible solution for the deadlock could be following. You could have some sort of a timeout. When a thread tries to acquire the lock, you just block for a limited period of time. If it's still unsuccessful, it will release any locks it may have already acquired. So for example, if thread 1 has acquired the first lock and thread 2 has acquired the second lock, thread 1 proceeds to and thread 1 proceeds to acquire the second lock. If it is still not able to do so in a certain time frame, it will release both the locks. It will release both the first lock and the second lock. Now, this solution may work sometimes, may not work at all, may not work at times. So it's not the right solution. So a possible scenario which could happen here is that thread 1 has acquired the first lock, thread 2 has acquired the second lock. Now, after some time, both the threads release their already acquired lock. So thread 1 releases lock acquired on mutex 1. Thread 2 releases lock acquired on mutex 2. And both of them again reacquire the same locks after a certain time period. So they kind of keep releasing their locks and reacquiring them, and they aren't in a deadlock, but they aren't also able to progress ahead. So they aren't able to do any meaningful work. This is called as a live lock. And because the term actually has its roots in the fact that the threads are not blocking forever waiting on the lock, but they are unable to proceed with their work package. Now, the most common solution for a deadlock and a live lock situation is that you acquire the two locks in the same consistent order. So if you acquire a lock on mutex 1 first, and then you acquire lock on mutex 2 first, lock on mutex 2 next, you always do so in both the threads, yeah, and then you release them in the opposite order. So this will help you avoid a deadlock situation. There are other wrapper classes as well that C++ provides. These are really nice when you are actually coding in a production environment. So there's stud lock guard, there's stud scoped lock. A lock guard is a RII wrapper over a simple lock, and it essentially is going to work in a way that uh, whenever you have acquired a lock on a mutex, you may forget to release the lock on the mutex. The lock guard class is designed such that its destructor will automatically release the locks on the mutex owned by the lock guard. So it's ensuring that it ensures that the moment the lock guard goes out of scope, the lock held on the underlying mutex object is released. There is a small code snip that I'd like to show here. So you have a function which always throws, which is called as function throws on line 9. There is a worker lambda function, which is again runs a loop and iterates 1 million times to increment the counter in a in a synchronized way. So there is you are guarding the incrementation of the counter using a mutex. And then there's another Lambda function called as worker exceptions. The worker exceptions attempts to do the same thing. However, it can possibly throw. So I've actually deliberately put in some evil code on line 27, which is always going to throw. And I spawn off 2 threads. You will find that while the worker is going to run fine, it's going to increment the counter value to 1 million. The worker exceptions thread will throw, but the lock acquired on the mutex will be automatically released, and there is no undefined behavior in when this program exits. The value of the counter will be 1,000,001 if you were to run this code snip. So it essentially makes exception handling easier when a lock is acquired. So there's also a scoped lock, by the way, which allows you to specify multiple mutexes. So if you ever have a situation where a piece of logic has to acquire locks on multiple mutexes, you can just specify it as a comma separated list to the scoped lock constructor. And all of those locks will be released when the scoped lock goes out of scope. There is another form of data race condition that can often occur. this is in classical computer science, this is called as the producer-consumer problem. Such a race condition occurs because of the fact that the producers and the producer and the consumer are producing or consuming items at different rates. And because the rates differ, they need to talk to each other and they need to have some sort of synchronization to ensure that whatever data structure they are populating, the data structure is not empty when you're trying to read from the data structure. All the data structure isn't full if you're trying to insert elements into the data structure. So in order to do this sort of synchronization, C++ offers something called as condition variables. Condition variable is always associated with a mutex, and it essentially allows for threads to wait for a notification from the other thread. So you would typically you can think of it as a publisher subscriber model where there is a publisher thread which is going to notify that a certain condition has been met, and the subscriber threads wait for the publisher thread and they wait on the notification, and only when a notification is received, they will go ahead and proceed with the task. There are so let me speak a little bit about the code snip that I have on the right. So there is a increment counter lambda function on line number 18. This is a fairly simple one, which runs a loop 20 times. Each time you just sleep for 100 milliseconds and then you increment the counter. You are guarding the incrementation of the counter by a mutex, so it forms a critical section. And every time you update or increment the value of a counter, you notify another thread using the condition variable. So you use the API call notify1, and there is another API called as notify all. The difference between notify one and notify all is that is simple. You basically want to express the fact that do I want to notify just any one of the threads? Do I want to wake up any one of the threads, or am I interested to wake up all the threads? So to have some control over that, you can use either of those functions. The next two blocks of code are wait for. So the next block of code is a function which is going to wait for a certain condition. It actually waits for a non-zero value of the counter. And the one on line 41 is going to wait for the counter to become 10. And what happens is when you start a thread T1, so you essentially start the threads T1 and T2. The thread T3 is the increment counter thread, and the increment counter thread is going to keep notifying one of these threads. So what will happen is that the moment the counter is incremented to 1, the wait for counter non-zero mutex thread will wake up, and it will print the counter is non-zero. And the moment the counter is 10, the wait for counter 10 CV thread is going to wake up, and it's going to print that the counter is 10. I'd like to draw your attention to the fact that line 43 has something called as cv.wait. So you are saying that I want to wait. Um, I want to wait uh, for the counter to become 10, which is specified in the form of a lambda function. So what happens is that wait for counter 10 uh, is going to lock the mutex. It will check whether the condition is true. If the condition is not true, the condition variable still remains in the waiting state, right? And it'll release the mutex right away, and it'll then keep on doing this. So it'll again after a certain time it'll go and it'll check. It'll try to acquire a lock on the mutex. It'll check if the counter is 10. Uh, if not, it releases the mutex and so on until this condition is met. So that's how condition variables can be used to wait for a notification or notify other threads that a certain event has occurred. I would now like to talk a little bit about how to design a basic thread-safe queue. FIFO queues are a standard way of communication between threads. And one of the use cases that I know, for instance, in the trading industry is something like this. So you usually have like two threads. One thread is a market data handler thread, which is constantly uh, uh, listening for network packets from an exchange place. And then there's a second thread, which is the actual trading application, which will run a certain trading strategy and send out orders to the exchange. The market data handler reads the packets from a network socket, and it builds a data structure called as the order book. And the order book is built for every symbol. So you would have an order book for Apple, you would have an order book for Google, and for each of these stocks. And every time an order book is built, it needs to be sent to the trading application. So the trading application expects a new order book, and then it will run a strategy on the order book each time an event occurs. So naturally, the communication mechanism between these two threads is a FIFO queue. The reason for having two threads instead of one is simply because it reduces the latency, and it has much faster performance. So let me talk a little bit about how you would go about designing a basic thread safe queue. So I'd like to talk about the interface first. So you would have typically a buffer, which is used to store the contents of the queue, which can be a stud vector, a mutex to synchronize access, uh, two condition variables, which are going to be used to notify if the queue is not empty or if the queue is not full. And then I also have variables to track the head and the tail of the queue. I also have a M capacity variable to indicate the capacity of the queue. The interface broadly consists of the following methods. So I've written a method called as front, which is going to give you the front of the queue, back, which is going to be the rear of the queue. Recall that elements get added to the rear of a queue and they get popped off the front of the queue. There is an isEmpty method, which returns a bool. There is an isFull method as well, which also returns a bool, and a size method. And I have four modifiers. So there's the two standard modifiers called push and pop functions. These are going to be blocking functions. And there's a try push and a try pop, which are going to try and push and pop on a best effort basis. Let's talk about the design of the utility functions that I have. So there's a number of ways that you could you could design your queue and test for test for if a queue is empty or a queue is full. The way I do it here is as follows. So initially, both head and tail are initialized to 0. At any time, if head equals tail, the queue is going to be considered as empty. So if they are both pointing to the same slot, they will be considered empty. If uh, if it is the case that the tail incremented by 1, so tail plus 1, if it is equal to the head, I'd say that the queue is full. Just for the viewers and listeners, this queue that I present here is a bounded queue. So it is going to have a fixed capacity, and it is actually much like a circular queue. So the head and the tail indexes will wrap around. The front and back implementation is fairly simple. I just read the head and the tail indices in the buffer. And finally, I have a size method. The size method either returns the difference of tail minus head or tail plus capacity minus head, depending on what are the relative positions of tail and head. So this is a fairly easy interface. Let me talk about the meat of the design, which is the push pop, the try push, and the try pop. Uh, the uh, the push is first going to try and acquire a lock on the mutex. In this case, I always acquire. So I'm always going to acquire unique locks because I want to design a single producer and a single consumer queue. So there's only one consumer, and therefore I don't have to share read access amongst multiple threads. So I'm okay to just use unique locks. Uh, as soon as I decide that I want to push something, I would like to wait on the not full condition. And the syntax for doing so is simply the condition variable dot wait. So I have on line 11 not full dot wait on the lock, which will, so this is going to be a blocking call, which is only going to return if the queue is not currently full. And then these are fairly standard statements. So I basically store an item at the tail index and I increment the tail by 1. And finally, I unlock the mutex. And the moment you've pushed something onto the queue, I would like to notify I would like to notify the other threads that the queue is no longer empty. So I use the not empty condition variable dot notify 1. Let's talk about pop, and then we can also have a think about how the push and pop are going to work together. So the pop is fairly similar. It essentially waits on a not empty condition variable. So it's going to block on the wait on line 11. It's going to store an item at the head index, and it is then going to unlock the lock acquired on the mutex. The moment an item is popped off the queue, it will, you're sure that the queue is no longer full. So the not full condition is now met, and therefore you will notify the other threads that the queue is not full. Try push and try pop are variants of push and pop, which attempt to do so on a best effort basis. So if you are unable to push an item for whatever reason, the function will immediately return. It will always return a bool, which signifies whether we are able to push or pop the item successfully. Let's move on now to writing a lock-free queue. While you can write or design a queue using mutexes and condition variables, this is not very performant. Using locks and mutexes requires or consumes additional CPU cycles and requires it essentially generates more machine code, and therefore, if you would like to write or design a queue in a more optimized way and write a performant queue, we can use the atomics offered by C++. So in order to design a lock-free queue, the first consideration should be, how are we going to write the interface? And I've put down an interface for a single producer, single consumer lock-free queue here. The first thing that you'd notice is that it has a capacity variable, which is a const x per variable. It actually uses a template parameter called as capital N. This is an exponent. So if I pass 4, I actually want to say that my capacity of the queue is 16. So it's one bitwise left shifted by 4. And if I pass in 5, my queue capacity becomes 32. If I pass in n, the capacity of the queue is 2 to the power n. You might wonder why I use a capacity of a power of 2. This is because when we want to increment tail and head, we always use a wraparound logic. And to use that wraparound logic, to wrap around these pointers, we use the modulo operation. The modulo operator requires a division instruction, which consumes several CPU cycles. So if it is a power of 2, we can avoid the modulo operation and we can simply use a logical AND like this. So if M capacity is, let's say 8, then if so current index, the next index can just be computed by using this instruction. The other consideration is about the alignment of these elements of the SPSC Q class. So I am specifically aligning them to a 64-byte boundary, and you might wonder why we would like to do this. This is because we want to avoid something called as fault sharing. And the idea behind fault sharing is fairly simple. Fault sharing occurs when threads on different processors modify different variables that decide on the same cache line. So as a simple example, imagine there are two CPUs. There's thread 0 pinned to CPU 0, thread 1, which is pinned to CPU 1. And imagine that thread 0 wants to read and read and write to a variable A, which is shown in red there, and thread 1 wants to read and write another variable B, which is shown in blue. Both the variables reside on the same cache line. Now, imagine a situation where both of them have read the variables A and B. So this cache line is the same cache line, right, is in the cache is in the on chip cache memory of both the cores. And now let's say that thread 0 modifies the variable A. When it modifies the variable A, uh, thread, uh, thread 0 or core 0 is going to put its cache line in the modified state, and it will communicate this to CPU 1. CPU 1 or core 1 will modify the status of the cache line as invalidated. And what happens is that if thread 1 now wants to reread the value of the variable B, it is not sure if B was changed as well because it's on the same cache line. So thread 0 is going to be forced to flush its cache or its buffer, and thread 1 will be forced to reread the entire cache line. And this results in a cache miss. To avoid this, you are just better off storing them on different cache lines here. So hardware destructive interference size is a C++ way of finding out what is the cache line size. On x86 machines, it is usually 64 bytes. So this line number 10 and 11 would read as align as 64 of the read and write indexes. The read and writes have been now declared as atomics, size T atomics. And on the next slide, let's look at how we can now write a lock-free queue. So here is the interface for try push and try pop. The push essentially is going to first load the write index. It also calculates what is the next index to be written to by using the logical AND operator. So we don't need to use the modulo now because capacity is a power of 2. On line 7, it is actually testing if the queue is full. And to do so, it reads the read index atomically. So the load instruction is atomic. For a brief moment, if we just forget about the argument to the load and the store function, so if you just forget about memory order, we can just think of it as read index.load. So line 7 checks if the queue is not full, and if it is the case, you write to the buffer. And what essentially needs to happen when you write a lock-free queue is you need to synchronize between the read index and the write index. That's something that we actually care about, and therefore I then atomically update or increment the write index to the next write index value, and I return true. Otherwise, I return false. Let's look at try pop. So try pop is going to read first from the read index. It then checks if the read index is equal to write index, which means that the queue is empty. Note that the write index is loaded atomically. and so at any given point of time, only one thread can load the write index, and you then actually store the you then move the result or copy the result from the read index into the buffer into result. And finally, you are going to update the read index because you have read or popped off an item. This this particular logic is going to work fine, absolutely fine, if we don't consider memory orders. But if I think about the memory ordering, is essentially says if instructions can be reordered by the CPU. An acquire memory ordering essentially says that instructions which are below the acquire cannot be moved above it. A release memory ordering essentially says that instructions which are above the release can't be moved below it. So the acquire release pair here forms a sort of fence. And so is the case with the try push. So this is a small demo of how you could attempt to write a lock-free queue which does not use mutexes. That's all from my side.
Thank you for this great talk. It was really interesting. And with that, if you have any questions, I guess they already have been answered in the chat, and otherwise put them in the comments on YouTube. Thank you for your time, Quasar.
Thanks a lot, Jens.